Good afternoon, everyone. You're tuned in to a presentation entitled, Actually, It Is Rocket Science, and subtitle Thrust Vectoring at a Model Scale. I'm Guy Gehlhausen. I'm a member of the NAR chapter Fox Valley Rocketeers in the northwest Chicago suburbs. It's a little warmer here today than it has been, so 20s. So all of you in warm weather that are watching, 20 is warm to us here. So just a few notes before we get started. You may chat among yourselves during the presentation. I probably won't be looking at the chat, but you can chat among yourselves and submit your questions in the Q&A on the right-hand side. You're probably getting the hang of that by now. And we'll try to leave some time to answer them. Because just another note, because this platform is web-based, you may notice some glitchiness or lag in some of the videos that I'm going to show. We've done everything we could to optimize them and compress them, but there still may be some of that going on. So it's not your TV set. It's my internet, your internet, and everything in between. So another note, I know the presentation says, actually, it is rocket science, but a bit about myself. I am not a rocket scientist or a controls engineer. I'm actually a licensed architect by profession and just happen to have a passion for anything that flies. So I do have a broad engineering background, so it wasn't a huge leap to understand some basic physics of thrust vectoring and rocket science and so on. So if I explain something about rocket science, it's from that point of view and that perspective. So if there's any real rocket scientists out there or controls engineers listening, if I start to explain what a PID control logic is, it's explained from how my brain works. So hopefully it's the way your brain works too. So I'm going to, without further ado, share my screen and bring up the presentation. So hopefully you're, excuse me, seeing me in the left-hand corner and the presentation there. So this is the rocket we're going to be talking about today. This is the model on the left, on the left, on the left, and then an actual photo of the rocket prototype on the right. So it's 1:48 scale, single SRB, and the model is thrust vector controlled. It's United Launch Alliance's Atlas 5 booster. 411 is the designation, means 1 4-meter payload fairing, 1 SRB, and 1 Centaur motor. And then the mission is the OSIRIS REx mission, which is still an ongoing mission, actually. The satellite landed on a asteroid Bennu, grabbed some samples and hopped off of it, and it's on its way back to Earth. And it's going to take a couple of years to do that still. Excuse me. So this story kind of has two parts to it. It started out building a scale competition model for NARM 62, which was supposed to be in 2020, but ended up being in 2021 due to COVID. And it ended up turning into a 2-year research project in how to integrate thrust vector control into this very unique rocket. Here you can see a drawing of the rocket and how this thrust vector control kind of integrates into the rocket. That's the gimbal unit and the flight computer there. This happens to be just a reprint, 3D reprint of the gimbal unit. They're all 3D printed parts. And so right about the time I started this project, there was a video that came out on YouTube and kind of went viral. Viral in the sense of model rocketry anyways. It wasn't Ice Bucket Challenge viral, but I saw this video of this Falcon Heavy model flying without fins, and I was wondering, how in the heck did this guy do that? Joe Barnard is the fellow's name that came up with this thing. So that system that's in there is what we're going to be talking about today. Also in relation to building the competition model, our local NAR chapter holds an annual event, kind of like NARCON. It's called NERCON. It's kind of a play on words. NI stands for Northern Illinois. But at NERCON, it's a one-day event, and we have talks kind of like this. And one of the fellows in our chapter, Ed Chess, did a presentation on what it takes to build a competitive model rocket for NARCON. And I'm sorry, NARUM, for NARUM. Too many acronyms. So Ed had a lot of sage advice. One was ditch the rattle cans. I still do use them, but ditch the spray paint and get a good airbrush, which I did, and fell in love with this thing. If you're a serious modeler, you got to have an airbrush. You can custom mix paints. The finish is much better. I forgot to start my clock. And so on. So it's a much better tool for final models. The other piece of advice that I took to heart and for this project was to build a boilerplate test rocket and fly it. Because in NARUM scale competition, you can't have grass stains or chipped fins on your model for static judging. So unless you're really confident, you probably don't want to fly your competition model. So that means building a replica of the rocket and flying it to make sure it flies okay, which I did. So just a bit about the prototype choice of the scale model to build. So this is my rocket room, the room I'm in right now, actually. It's rearranged a little bit as a video studio right now, but I literally have built hundreds, I don't even know how many there are. There are probably 200 airplane and rocket models in that room. And most of them are scale models, and I've built lots of scale models, but as you can see, they all have clear fins up until the point where I had the thrust vector system. So this is excuse me, a Titan series, Delta series, 2, 3, and 4, and the Atlas 5 series. This is actually the one that I'm going to be talking about at a much smaller scale, but all have clear fins. So as I mentioned, about the same time, this thrust vector system came out, and Joe Barnard began to sell them. And I took a leap of faith and bought one. I was so enamored with the potential of this to actually do a model rocket, a scale model rocket without fins. And let's see, where am I at? So this is the flight computer here on the left, and this is the mounts that it fits in a 3-inch apogee thin wall airframe tube, so it's made for that. And I had a bunch to choose from, and I was trying to come up with something that was interesting, had a good story to it. And these are all models that I had built, and ended up obviously selecting the Atlas V. One of the criteria is because it's a 3-inch airframe, once you scale up, you couldn't have a rocket that is thin and tall, because by the time you scale up 3-inch diameter, it couldn't be 8 feet tall or something. So that played into the selection. And obviously this rocket, Atlas V 401 OSIRIS REx, had a neat backstory. And I had this vision for a long time of replicating the slow liftoff and flight of a liquid fueled booster. They always look like they're almost standing still when they go off the pad. And always a big exhaust plume with a liquid fueled rocket. It's mostly steam, though, from the sound suppression system. So I had this idea that I would try to push the limits of the thrust to weight ratio as close to 1 as possible and have it still fly. And you can see these lines are the thrust to weight ratio of these rockets approximately at liftoff. Now, obviously, a liquid fuel rocket, the thrust to weight ratio is increasing rapidly even as it goes clears the tower. But and it's not quite the same in a solid fuel rocket. So before I even started building this, I had done some modeling on Open Rocket and came up with a mass and target mass, and using these two engines, these two motors, the F-15 in the core and E-12 in the SRB. So I graphed using about 1,350 grams was my target. The thrust to weight ratio using that weight of what that flight profile would look like. And as you'll see, it turned out to be pretty darn close to how it actually turned out. So I was building a rocket with a target mass and a target thrust to weight ratio as low as possible, or as close to 1 as possible, and still fly and get up in the air. I also, to find out a little bit about what NARCON was about, because this was the first time I'd done this, excuse me, went to NARCON 61 in Muncie, Indiana, and to kind of as a visitor, or not a competitor, to see how the scale competition worked. And my takeaways were I was definitely going to have to be on my A game in building this rocket, for one, and second, when I watched all the flights, and there was one video I'll show you here in a second. It's a model, excuse me, it's a Vostok with 5 motors in it, and the takeaway of this is don't try to light 5 composite motors. And I'm showing this not to embarrass anybody. In fact, I don't even know whose rocket it is, but it was a great lesson in my motor choice for the scale competition. This might be a little pixelated on your screen, I'm not sure.
So disqualification for unsafe.
So Mark, if you're watching, Mark Bundick was the RSO that day. So a little bit of background about the rocket itself, the prototype. My wife and I like to head to Florida and visit our family a few times a year. I always try to look up the launch schedule at Kennedy Space Center and see if we can coordinate it around running over to Kennedy Space Center. And this visit in September of 2016, just a serendipitous visit, honestly. We were staying at the Cocoa Beach Hilton one night, went out to dinner, came back, and the parking lot was packed and couldn't figure out what was going on. And it turned out to be the pre-launch party for this launch. So my wife and I said, okay, well, we just hung around with the party, and I think it was a cash bar though. But anyways, not one person all night asked us who we were or anything. Collected the bling and nice poster and some other things that they were handing out, and no one asked us until we were riding up in the elevator to go to bed that night who we were, and I had to say I'm just a rocket nerd here for the launch. So here's the actual launch. We observed the launch from LC-39 observation gantry, which is an Apollo era observation area. It's really close as any general public can get to pads 39, 40, and 41. It's only about 12,000 feet. If you recall, about that time, a week before this launch, SpaceX blew up a Falcon 9 on the pad. And there was fear of damage because these pads were so close together, but fortunately nothing happened. So turn up your volume. This is a few seconds of this launch. So at that distance, you can really feel the rumbling in your chest. I highly recommend that if you can get a chance to watch a launch from the LC-39 launch gantry, I highly recommend it. So here's some photos of the actual rocket on the pad right before launch. Now, one unique attribute of this rocket is this, this single SRB puts an off-center thrust and off-center asymmetric torque on the rocket. And you can see here's about the center line of the strong back, and it already has slid off to the side because of the correction that the canted nozzle on the SRB and the thrust vector system needs to do to correct for this off-center torque. Some of the challenges of the model were mainly the anodized aluminum colors of the boosters. If you've ever noticed, the Atlas V has, depending on which one it was, they have different colors. And it's the anti-corrosion treatments that they put on the aluminum. It changes color to a copper color over time. So if it's fresh out of the factory, it'll look more aluminum colored. If it's been out in the sun and weathering or aged, it's more of a copper color. So here's a little diagram of what United Launch Alliance calls this rocket the slider. And the reason it's a slider, as I showed you before, is that it literally slides horizontally. And that is due to this asymmetric thrust of this SRB puts asymmetric torque or a moment on the rocket, and a rocket reacts around the center of mass. And then to correct for that, the SRB has a fixed thrust vector of 4 degrees. So it's putting a force on the rocket at the tail end, trying to turn it back this way. And then whatever it can't handle, then the thrust vector system of the RD-180 also pushes it this way. So if you remember your vector math from a long time ago, if you add up the horizontal, break these down into horizontal and vertical vectors, add them all up, you end up with a net horizontal vector due to this correction. So it's small, but enough to slide the rocket horizontal. And the model actually does exactly the same thing. And I just wasn't sure exactly how it was going to react. So I'll show you some of that in a minute when I get to the boilerplate. So I just added these slides. Last week, ULA launched an Atlas 511, which is the same booster as the model that I did, except it has a 5-meter fairing, 5-meter fairing. So ULA calls that the big slider. And Tori Bruno is the CEO and president. He's also a rocket scientist. He can explain this a whole lot better than me. So here's a video of him explaining some of the rocket science here.
Hi, I'm Tori.
You might need to turn up your volume.
I'm here to talk to you about our upcoming mission, USSF-8. This is a really cool mission. We're going to launch 2 spacecraft directly injected to a high-energy, near geosynchronous orbit. And a lot of you have asked about the configuration of the rocket that we're going to use. Well, this will be the first flight of the big slider, the Atlas 511, with only 1 solid rocket motor. And we call it the big slider because if you watch the launch, you're going to see it kind of power slide off the pad because of this asymmetric torque. And a lot of you have wondered, well, how do you fly that? Well, that nozzle is canted to pass through the average center of gravity. And the RD-180 has tremendous control authority with this thrust vector system, and it can overcome that and compensate for it. And this is just the right amount of energy to carry these 2 payloads to their very cool mission, space surveillance.
Okay, so that is what I had to deal with in the model as well. So here's the components of the Atlas 5411. So there's the Common Core booster, the single SRB, Centaur second stage, and a 4-meter fairing, and of course the satellite. And the rocket flies with a Russian-built RD-180 engine, which is actually a very powerful, reliable engine, really high thrust to weight ratio, almost 1 million pounds of thrust. But unfortunately, it's not real politically correct these days. So in their new Vulcan booster, which will replace this and the Delta 4, they will be using a different engine, the Blue Origin BE4, 2 of them. This is the single SRB. I worked very hard to model this part attachment here on the final model too. Here's the payload fairing, the ribs, some of the markings. And that's actually the satellite, the asteroid that the satellite went to. So the model design and construction. There's the components. So I did a lot of research to gather dimensions for this scale rocket. And early 2019, I thought that the competition was going to be scale competition as opposed to sports scale. Scale, which it was in 2019, and I thought 2020 was going to be that. So I started out building this model as if it was going to be a scale model and exact scale. So I gathered dimensions from about every place I could, even the ULA user manual, and then extrapolated from photographs, the ones I couldn't get directly from literature, and then used the diameter of the final model, just a little over 3 inches, to create a factor, a scale factor, and then extrapolated all the other dimensions. So I didn't find out that until the end of NARM, 2019 NARM, that it was going to be sports scale. So some of these dimensions weren't as critical, but I still did need these dimensions. So, and of course, being an architect, whenever I do a big project, I draw everything to scale. So it's all worked out on paper, basically my own directions on how to build it. These are some of the some of the drawings. A lot of the parts were 3D printed, the aft engine section, nose cones, nozzles. And so I needed to do exact dimensions down to the 100th of an inch for the 3D printing. And I actually, I did not print them myself. I used Alex Boise at Boise Aerospace, who has really great aerospace models, has really high quality printers, and there's no way I could ever afford printers like that. So it's worth it to me to have someone print them for me. So you remember that diagram there and of thrust to weight ratio. So as I started construction, I was trying to get between 1,300 and 1,400 grams. Well, the first one I built turned out to be way too heavy. I used more common materials, the PML quantum tubes, which are great product, but this ended up weighing about 1 pound too much. So all the brain trust at Fox Valley Rocketeers came to my assistants and gave me a paper written by Chris Flanagan, actually, on how to make custom fiberglass tubes out of sheet fiberglass. And this happens to be out of black fiberglass, but it's one that was not the right dimension. But you can see you wrap it and seam it with a strip of fiberglass and epoxy. So here is the rocket under construction. And I didn't use black fiberglass on that one. I used clear sheet. But the bottom section is made out of 15 mil fiberglass sheet. The upper section is 10 mil. Some of it has a little bit more durable phenolic tubing because the pyro section is right here, and I didn't want to blow up the 10 mil section. And then here you can see some of the, it's kind of see-through at this point. Oops. You can see the avionics bay right here. That's the flight computer, thrust vector system, batteries up in here, and you see some reinforcing rings in there. But this did it. Chris Flanagan saved the day, and this came out weighing right about where I needed it to be. Some of the details I used polystyrene rib strips like Evergreen or Plastruct. That was quite a chore to mark those ribs and glue them on. I used some wraps. That is also some Evergreen plastic for the spray-on insulation on the Centaur stage. And this is the avionics bay here. You can see in here the flight computer. It needs to have a hole in the side because it needs to get air in the side of the rocket for the barometric altimeter. So there were 4 little holes screwed into the side of the rocket in the final model. And there's a lot of wiring that goes on here. I use all quick connect stuff so that, because these rockets have to be taken apart in at least 4 different places. So you have to kind of plan for where your seams are going to be. And I'm running out of time, so I'm going to not cover this, but these are some of the attributes of the model. If you do want to get a copy of this presentation, there's PDF available. So here is the final model, and you can see it turned out to be pretty darn close match. I impressed myself actually with the color mixing. And here is the payload fairing, some of the details, the liquid oxygen transfer line, some of these little components here that where the SRB sits. I made a master out of plastic and then made a mold and resin cast because they were really a pain to build. So there's 5 of them. So I only built 1. And this is the SRB. Probably spent more time on the SRB than the other part of the model. It was such a critical component of the rocket. It's quite a little thing in itself. So thrust vector control. So as I mentioned earlier, a rocket moves about its center of gravity or center of mass. So if a rocket turns this way and has torque on it in this direction, you need to push the rear end in the opposite direction. So so that's how thrust vectoring works. And in the case of the single SRB, I explained this a little bit before, but you've got this off-center thrust that's probably in the model 2-inch arm here. So it's wanting to push the nose of the rocket that way. So I had to build into the SRB of some fixed vector. The most I could get is about 2 degrees by canting a 24 millimeter tube inside a 29 millimeter tube. And then, so that is pushing that way a little bit. And then the thrust vector system has to do the rest. And here you can see, this is a photo of one of the boilerplate rockets, and you can clearly see that it is pushing or it is angled this way. The BPS thrust vector system has 5 degrees maximum. And when you look at the data, the flight data, about the first half second or so, it's all the way over at full 5 degrees. So again, these are the components that get integrated into the rocket. That's a printed circuit board, a PCB with all the components. And then the 3D printed thrust vector system. It has 2 servos, 2 9-gram servos. And then the wires go up and connect to the flight computer. It has 3 different pyros you can use also, so you have some options there. And here it is in the actual components. This is actually a reprint. The original was gray, but it's a reprint. I can't remember if this one's ABS or polycarbonate. I've used both. But it's a reprint, and it uses inexpensive servos. Those are just $2.99 servos from the hobby store. So how does the controls work? So it functions on what's called a PID controller, or control logic, and stands for proportional, integral, and derivative. And I'm not going to be able to get into a big, long definition here because I don't have a whole lot of time. But every rocket is unique. And these are the parameters that you enter for each unique rocket and to tune the rocket. So there's the loaded mass, that's flight ready with everything, motor, parachute. So this particular rocket was, that's in kilograms, so that's 1,236 grams. You take some measurements, the distance from the center of mass to the TVC mounting screws. It calculates the inertia of the rocket, and I'll show you in a minute, but you have to do a swing test on it. And the secret sauce in the BPS flight computer uses these dimensions, and then you measure the rotation time, in this case 1.8 seconds, and then you give it the average thrust. I had a lot of internal debate on whether to include just the thrust of the F-15 core motor or both of them, and ended up settling on the logic that the F-15 core motor really is the one that had the authority to vector the rocket. So I used the average thrust of the F-15, which turned out to be the right answer. So once you enter these parameters for each rocket, it calculates, the flight computer calculates the PID values. And then those PID values are used to, obviously for corrected measures during flight. And it functions at 25 hertz or 25 times a second. It sends commands to the X and Y axis servos. We doesn't have any roll control, so no Z axis, but X and Y only. So here it shows the how you do the swing test. You hang the rocket from a couple strings. Center of mass is about here. You measure distance from there to there, the length of the string, the length from center of mass to there you can see the thrust vector screws. And then you swing it back and forth around the center of mass, and it goes back and forth, and you count how many times it swings. I usually do at least 10, maybe 20, and take an average. So again, what a PID controller is, P stands for proportional. So it's just a fraction and a percentage of the error. In that case, it was about 30%. So the P I kind of think of as the workhorse. And then the I integral is a term that corrects for error, accumulated error. And that one, what it does is there's a couple errors that are almost always built in every launch, and that's you have to align the XY servos and get them straight. Well, you can never really quite get them perfect. You might be off a degree or two. And then D, the derivative, is a term that tries to predict the future, and kind of, I always think of it as kind of dampening out too aggressive of maneuvers, an overshoot, and so on. So it kind of smooths out the flight. So those three values multiplied together at 25 times a second is what controls it. So common uses of PID controllers are all around you. Your automobile cruise control uses them. A good quality commercial thermostat uses them. The only difference is what is the set point. So obviously on a cruise control, speed is the set point. On a thermostat, the temperature is the set point. And the thrust vector control, vertical, is the set point. So it's just trying to hold that set point. And like I said, this is in the PDF version. I'm not going to have time to really go through those in great detail. So the flight computer records flight data, which was super valuable during this process. I use this every flight to diagnose things or even find out things I didn't know were happening. And it's there's a lot of data points. It's logged at 40 hertz or 40 times a second. And there's a little micro SD card, like a camera card, on that card is recorded in a comma separated file or a CSV file. And then you just take it out, put it in your desktop or laptop, and do a save as an Excel file, and you can you've got way more data than you'll ever need. In this case, I highlighted some columns because I'm usually looking at G's in the Z-axis. It's in metric in here, and then I have to add the force of gravity in there to get to G's. And then also altitude in meters, and I have to convert it to feet. So this is what kind of zoomed in on the data. In this case, I couldn't figure out why the pyro was firing a little early, the parachute deployment pyro. Well, it turned out that it was changing modes and in going into burnout mode, because when it detected this only happened when I started using a larger E12 in the SRB, but it was thinking that the core motor had burned out. So it went into burnout mode and then fired the parachute. So that wasn't what I wanted. I wanted the burnout of the core motor to be what deploys the parachute. So it was a pretty simple fix. From then on, I used the timer mode. I knew about 4 seconds would be about right. So that fixed that. So now the boilerplate test program. So I had a bunch of different versions over time because I crashed them. And it started out looking like a Delta 4 medium. And of course, it never had an Atlas SRB on it, but that's okay. And I always like to paint my rockets to look cool. So even though it's just cardboard tube and a nose cone, and so the next version looked like that, and the next version looked like that, and the final version was actually very close to mimicking the actual scale model. And this is the mobile launch pad that I built. It actually is kind of a semi-scale model that is a combination of the Kennedy Space Center mobile platform and the Vandenberg Air Force Base pads. So that I had the strong back here, has a flame trench in it, sheet metal flame trench that shoots the smoke out. I even have a little 1:48 scale Torrey Bruno with his signature cowboy hat over there. So here you see the smoke shooting out, and that's one of the reasons for using black powder, sticking with black powder motors to mimic replicate the exhaust from a sports or from a scale rocket, a real rocket, I'm sorry. So here's some of the flight data recorded on top of each other. As I flew these test rockets, I was working my way up with thrust motors, increasingly more thrust in the SRB, because I didn't really know what was going to happen. So I used B's and C's and D's and finally to the E. And this is some recorded data all graphed on over the top of each other. Excuse me. So here is that graph that I showed you earlier that I had done before I even started construction of the model and what I thought was going to happen. But what I kept getting 3-second flights or 3-second burn times pretty consistently. But an F-15 burns 3.5 seconds. So in correlating the slow motion videos and the data, I figured out that what was happening was actually the motors didn't generate enough thrust until just when the flight computer clock runs at about a tenth of a second. So about a half second before those motors had enough thrust to get the rocket moving. So I did find out also that pretty consistently you need at least at this high point of the initial thrust spike of a black powder motor, around thrust to weight ratio of around 3, and a sustained thrust to weight ratio of about 1.5 to get a rocket to fly. So that's about the best and closest you're going to ever get to mimicking a liquid fueled rocket with solid motors. So I figured out also pretty quickly that I needed a checklist after screwing some things up. So I developed this pre-pad checklist. In other words, this is stuff, this was all stuff that I did before I got to the field. And then things can happen in the car on the transport. So there's another check of things to do in the field. I knew this actually happened when I had actually lost continuity on the pyro, the parachute pyro. So from that point on, I double checked that and a lot of other things. I also did some ground testing. I don't really have time, I don't think, to go into it, so I'm going to have to skip over that. So there was, I did 6 proof of concept flights. In other words, I just needed to find out if this project was even viable and I could get it to work, which I did with, progressively higher thrust in the SRB motors. And then I did at least 12 boilerplate test flights. And those were ones where the rocket was relatively close to what the final scale model was. So this is the first test flight. It's only the core booster, and everything worked fine. And it was relatively windy and it flew okay. That might be a little glitchy and pixelated. And you could see how far it drifted down range just from the wind pushing it. So it worked fine without an SRB, but I was really worried about what was going to happen when I strapped a motor 2 inches off center on this rocket. So this is just a little sketch, a little diagram of a quick way to vector some thrust in just a thrust vane, which I'll show you in a second how I did that. The first try, I measured that the angle between the thrust of the SRB and the center of gravity was about 10 degrees, and a little more than I expected. But I said, okay, well, let's see what happens if we put a 10-degree vector on the SRB motor. So there's just a sheet metal plate at 10 degrees. So what's happening there at 30, if the rocket goes 30 degrees out of vertical, there is a in-flight abort mode that fires the pyro parachute pyro. So you get your rocket back and it's unbroken. So it's a pretty nice feature. Used it a number of times. But I wish some aerodynamic rockets had that feature. So then, so that I figured out that, maybe we don't need to do that so much. So this is just a quick test with a C6 in the SRB, not a lot of thrust, but everything worked fine. And the SRB was jettisoned, came back on a streamer. And also, I was moving up the scale here and on the SRB motors, and this is a C11. But what I found out is that it separates way too quickly. And also this one, the parachute tangled, and so I lengthened the shock cord and changed my parachute packing. So I had been posting to social media my exploits in this project, Twitter mainly, and this flight here, someone must have sent it to Tori Bruno or retweeted it with a hashtag Tori Bruno. And I actually got a direct response from Tori, got a wow, nicely done. So I thought that was pretty good. But last night at the keynote speech, they were talking about the power of social media. And I can tell you, it has impressed me by doing this. So I don't know if you're watching closely there, but the rocket kind of rolled a little bit, probably because just something wasn't straight, but it looked cool. Uh-oh. Uh-oh, I'm sorry. I crashed here. I'll be back in a minute. Okay, hopefully I'm back. I didn't stop sharing, so hopefully I am still sharing. So I was continuing to test various things. This is where I stepped up to a D motor, and I was using the SRB strap-on booster mounts from Apogee. I didn't want to reinvent the wheel, so I was just using those cast resin attach points from Apogee. Well, I don't think they're made for this much thrust. They broke. And here you can see the SRB kind of flapping in the breeze. I also tested a Mylar chute, which turned out to be a great little thing. It's 48 inches, 16 shroud lines. So this is a dusk flight where I used, this first time I used an E12 in the SRB. I gotta make sure I'm still sharing here. So this is the first time I used both the full thrust and full mass of the rocket. Flew well, nice and straight. And this was, you know what? I'm running out of time, so I am going to jump over some of these flights. Lesson learned, broke a shock cord, so I used a double shock cord from here on out. One of the final flights, I flew in 20-mile-an-hour winds, found out it flew fine. It just gets pushed downwind. And here you can see the gimbaling to correct for that thrust. And an almost final boilerplate. I was trying a new chute, a sphere chute, which are really cool, but unfortunately I tangled it and lengthened the shock cord, which cured that. And the final boilerplate test, this was, everything went great. I literally pulled out the flight hardware, put it, this was maybe in June last year, put it in the final model, scale model, and didn't touch it till NARM. So NARM, here we are at the sports scale competition in static judging. There was really some beautiful rockets there. And I think after static judging, there was 3 or 4 models that were neck and neck. So anything could happen at flight day. I also included a diagram because I don't think thrust vectoring had been used at a competition before. So I wanted to illustrate some of the safety features and how that rocket was going to fly the next day. And here we are just a little bit before launch. And at this point, I had done so much testing, failure was not an option. If there was something going to go wrong, it was going to be pilot error, and it was going to be me that was going to do it. So that's Gene Kranz, he's the man. And so that day I did my checklist twice. I wouldn't let my wife talk to me hardly. Anyway, so here is the launch at NARM. If you listen carefully, there was actually 2 pyros there. There was a backup pyro as well. Okay, so I'm almost done here. I ran out of time. Again, social media, I posted that video that you just watched and got a nice out of Tori Bruno. And I also have a NASA astronaut that followed me on Twitter and asked me some questions about how I did some of the details and so on. So I thought that was pretty cool. So what's next? I don't really have time for that right now, but I ran out of time here, unfortunately. So I am going to go back to the video. So I've got, let's see, were the first questions last or at the top? I'm not sure. But anyways, I've got hardly any time for questions, but I will answer them best I can. You can hang around. I will hang around and answer the questions. If you have to go to another presentation, go ahead and do that. But I will hang around and won't stop the broadcast until we get your questions answered. So Andrew says, where did you get and how did you make the 10 mil tubes? ACP, is where I got them. And ACP Composites, there's some supplies right there from my next model. And there's a little bit of a process to that. If you emailed me, I'm sure I could tell you a little bit more on how to make them. It's a little bit of a process, too much to explain here. It's not that bad, not that hard though. So Robert says, since the thrust vector only works while under thrust, does momentum keep it flying straight after burnout? No, it does. Well, to some extent, but if it does have some aerodynamic qualities to it, it may fly relatively straight, but usually they just kind of tumble once the thrust ends. If they're really out of, really non-stable, they just tumble. So Kurt, hi Kurt. Kurt says, maybe address the importance of diverse angles of video at each test launch. I know what he's talking about there. He has videoed a few of my launches from different angles, and it has helped because you know which axis something went wrong in, X or Y. He's also been in the wrong place at the wrong time on a few launches too. Tom asks, are you willing to share your flight computer data? Sure. I have no problem with that. It's non-proprietary by any means. Again, if you email me, I'd be happy to share my email address. You might even be able to get it here at Excel Events, but it's simply my name, Guy Gehlhausen, at AOL.com. I'm kind of dating myself there with the AOL, but so no dashes or hyphens, just GUYGEHLHAUSEN at AOL.com. And I can absolutely send you some Excel files or whatever format you want. David asks, how hard did you have to chuck the scale? Wait a minute, what happened here? What happened to that question? How hard did you have to chuck the scale asteroid to get it into orbit? Nice. David, wonderful job on the project and presentation. Thank you. Tom asks, you said you have a PDF version. Yes, you can get that from the Excel Events. I know Todd uploaded it. I'm not quite sure how to download it, but yes, there is a PDF version downloaded. And Thomas, great presentation. Thanks. Well, thank you. And if there is no more questions, we're a little bit past our time. So I will sign off. Thank you all for watching.